Let us consider now a few examples of linear dependence or independence. Examples. So first, let's take S to be the set of just one vector, V. Okay? V in a vector space. So when is S a set of linearly independent vectors? So we go back to the definition of linear independence, and we have to consider a linear combination of vectors in S which gives the zero vector in V, and see when this is possible. Okay, so a linear combination of just one vector is simply a vector multiplied by a scalar. So a linear combination of one vector is just nothing else than lambda times V. Okay, so now let us assume that lambda times V equals the zero vector in the vector space. Okay. Okay, so all the coefficients of the linear combination must be zero. Here there is just one, which is lambda. So when does this imply the lambda must be zero? Well, this happens just if V itself is different from zero. Okay. So this happens, if and only if the vector V is non-zero. Okay. Let us assume that V is zero. So if the vector V is zero, then any lambda times V will give the zero vector. Okay, so in particular a non-zero lambda. Therefore, if V is zero, the set of just the zero vector will be a set of linearly dependent vectors. Okay. So a set comprising just one vector is a set of linearly independent vectors if and only if the vector is non-zero. Let's consider now a set of two vectors S. Let's call them V1 and V2. Okay, in a vector space V. Now a linear combination of two vectors can be written explicitly as follows: lambda 1 times V1 plus lambda 2 times V2. Okay. Now let's assume that this linear combination is the zero vector. To see when the set S is of linearly independent vectors, let's see when it is of linearly dependent vectors first. Therefore, we assume that there exists a linear combination as such for which one of the two coefficients, lambda 1 or lambda 2, is non-zero. Okay, so let's just assume one of the two is irrelevant. Assume lambda 1 is different from 0. If lambda 2 is different from 0, it's just the same. So now we are in the assumption that S is a set of linearly dependent vectors. So if they are linearly dependent, then we can rewrite this expression as follows: lambda 1 V1 equals negative lambda 2 V2. This always holds. Now we use the fact that lambda 1 is non-zero. We can divide by lambda 1 both sides of the equation. So v1, we can actually explicit v1 in function of everything else. So negative lambda 2 divided by lambda 1 times v2. Okay, so if there exists a linear combination, a non-trivial linear combination giving me the 0 vector in v, then v1 is a multiple of v2. Vice versa, if v1 is a multiple of v2, therefore v1 is alpha times v2, then I can clearly find a linear combination, non-trivial linear combination of v1 and v2 that gives me the 0 vector, namely then v1 minus alpha v2 equals the 0 vector. Okay. Therefore, this shows that two vectors are linearly dependent if and only if one is a multiple of the other. Negating this statement is just as saying as a set of two vectors is a set of linearly independent vectors if and only if one is not multiple of the other. Conclusion, so therefore S is a set of linearly independent vectors if and only if v1 is not a multiple of the v2. Okay, so in the case of set of one vector or set of two vectors, linearly independence is very easy to check. It doesn't require any computation at all. Okay, we can just do it by sight. In the case of vectors are vectors in Rn, let's say. Okay, let's see three vectors. The case of three vectors. The case of three vectors is the first one that can be actually generalized to an arbitrary number of vectors. Let's see then, so v1, v2, and v3 in a vector space V. Then what does a linear combination look like? So it's going to be something like lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 equals to 0. Again, let us assume that these vectors are linearly dependent first, and then we negate that condition to see when they are linearly independent. So they are linearly dependent if and only if there exists a linear combination as such that gives me the 0 vector, and one of these coefficients is non-zero. Let's now assume, for example, then that lambda 2 is non-zero. Assume this time, assume that, let's say lambda 2 is non-zero, then, well, I can play exactly the same trick as before. So I can explicit v2 in function of everything else. So v2 is going to be equal to what? So I have to divide by lambda 2, which I can do because it is non-zero by assumption. 1 over lambda 2 that multiplies negative lambda 1 v1 negative lambda 3 v3. And these can be expanded as negative lambda 1 divided lambda 2 times v1, negative lambda 3 divided by lambda 2 times v3. So once again we expressed the vector whose coefficient in the linear combination was non-zero as a linear combination of the other two vectors. Okay. So vice versa, if v2 is expressible as a linear combination of v1 and v3, let's say alpha 1 v1 plus alpha 3 v3, then I can certainly find a non-trivial linear combination that gives me the zero vector in v of these three vectors. Namely, then we have negative alpha 1 v1 plus v2 negative alpha 3 v3 equals to 0 in v. So here is the linear combination whose coefficients are, the first one is negative alpha 1, the second is 1, and the third is negative alpha 3. Therefore, we can conclude that for three vectors, we have that they are linearly dependent if and only if one is linear combination of the other two. Therefore, they are linearly independent if and only if there is no vector inside which is linear combination of the other two. Okay. Therefore, S is a set of linearly independent vectors if and only if no vector in S is a linear combination of the others. And this is true in general for any number of vectors. One very important remark is the following. So if one of the vectors in the set S happens to be the zero vector, then automatically the vectors will be linearly dependent. Okay, so if the zero vector in V belongs to S, then S will be a set of linearly dependent vectors. So how do we prove this? Let's just take, for example, any other vector in S. Okay, if it is the only vector in S, then we know that is linearly dependent because it is just the case of S being comprising just a unique vector. So if there are at least two different vectors in S and one of them is the zero vector, then pick another non-zero vector V, and we can have a non-trivial linear combination of V and 0, giving the zero vector. Indeed, pick a V in S, a non-zero V in S, okay, and consider the non-trivial linear combination given by 0 times V plus a non-zero scalar, let's say 1, times 0. Okay, so this is the zero vector. So what do we get here? So this is the zero scalar times V, and this will be 0, plus 1 times the zero vector, and it will also be the zero vector. Therefore, the sum of 2 times the zero vector is still a zero vector. Okay, so we have a linear combination of two vectors inside S, which is non-trivial, and gives me the zero vector. Therefore, the vectors in S will be always linearly dependent. So if you want a set of linearly independent vectors, we cannot have the zero vector inside of it.